One of the first forces that we are going to look at is the force of gravity. Now, again, as stated previously, we don't actually know why gravity exists, which is one of the more fascinating aspects of physics to me, because it's the force we experience in our everyday life. So, we are going to go into it to a minor degree at the moment. Later in the year, we will take a much deeper dive into what we know about gravity. But for the moment, we just have to understand the following. You're going to hear two terms, mass, and you're also going to hear weight. They are not the same, but they are very closely related. It's very important to understand the distinction. So, the way I kind of explain this would be to state that mass is the measure of the amount of matter making up an object. It's a measure of how many molecules, how much stuff makes up that object, that compound, whatever you're talking about. Weight is really the force of gravity. So the term weight is interchangeable with gravitational force or force of gravity, and it's the actual force that is acting on that matter. So mass is how many things you have, how much matter you have, and weight is the force of gravity pulling on that matter, or the force of gravity acting on that mass. So they're very closely connected, right? I like to show this visual because you can see each individual particle, each individual molecule gets its own little arrow representing the force of gravity. Because the Earth's gravitational field, Earth pulls down on each of those molecules individually. So when you have more of those molecules, you're basically adding more of those little arrows. So more molecules means more forces pulling down and more weight. So when you have more mass, do you have more weight? Yes. Because if you're made up of more things, you have more things being pulled down by Earth's gravity. Are mass and weight, or mass and the force of gravity, the same? Absolutely not. But a lot of people interchange those words as if they were the same, and that is something we have to make sure no longer happens from this point forward. So, one of the big things is that your mass, which we measure in kilograms, remains constant. Unless you like break pieces off, you shave pieces off, or something like that, you physically remove particles, your mass is constant. So if I have a mass of 90 kilograms on Earth, I have a mass of 90 kilograms on the moon, and 90 kilograms on Jupiter, and 90 kilograms anywhere in the universe. Unless I literally like lose some molecules, okay? The weight, however, in this case, the force of gravity, which we measure in newtons, that changes based on your location. Okay, so if you go to the moon where gravitational acceleration isn't 9.8, it's about 1.67, I will weigh less. And that's this instant weight loss on the moon. It's one of my favorite jokes. Hey guys, we could just make like a crazy weight loss program, right? Hey, join our weight loss program. We'll send you to the moon. It'll be great. We'll make so much money. But you know what? It's probably not going to work that well because you know what? Honestly, once everyone goes back to Earth, they're just going to gain that weight right back. Okay, anyway, yes, it's okay to laugh at that because that one was pretty funny. It was actually a Walkowicz original. All right, anyway, so, right, I go from Earth to the moon, moon to Earth, Earth to Jupiter, Jupiter to Neptune, etc. Every time I go somewhere where there is a new acceleration due to gravity, 9.8 on Earth, 1.67 on the moon, about 23 or 24 meters per second squared on Jupiter, now my weight is actually going to start changing. And that's the really important distinction. If people use mass and weight interchangeably, they're going to get the answers wrong because mass is constant throughout the universe, assuming you don't break pieces off, and the weight changes based on what you're next to, what gravitational fields are being produced by the masses that you find yourself in. Okay, so where am I going with all this? Well, we need to be able to understand how to convert between mass and weight. The good news is we do that using Newton's second law, so it's not new information. What we just have to realize here is the following. Newton's second law says F equals ma, and we're just going to go ahead and adjust that. Instead of just saying F or F net, we're talking about gravitational force. So I just replace it with Fg. And instead of just saying acceleration, which it is, we're going to say the gravitational acceleration. So like negative 9.81 on Earth. And I'm going to replace that. So F equals ma really becomes Fg equals mg. Same equation. It's force equals mass times acceleration, but it's gravitational force, which is weight, is equal to the mass times the acceleration due to gravity at your location. Okay, so let's look at an example. You're asked, how much does a 15 kilogram mass weigh on Earth, and how much will that same 15 kilogram mass weigh on the moon, where your gravitational acceleration is about a sixth. It's about 1.67 meters per second squared. It is negative. you're going to find from this point forward, I kind of throw that negative away. It's implied that gravity acts downward. So I'm going to commonly use G as a positive value, and then in my free body diagrams or my analysis, I'm going to represent it as going downward. That's kind of like a common thing. But if you want to include the negative, you certainly can. All right, so how am I going to figure this out? All right, so we know that the mass, we know that the mass of this object is 15 kilograms. It's on Earth. Okay, it's on Earth. So on Earth, we know that the acceleration due to gravity is 9.81 meters per second squared. Yes, it's negative. Again, just to reiterate, I'm going to generally write it as positive, and then we will use an arrow to represent that. And here's what I mean. Ready? So we know that Fg, the weight or the force of gravity, is just the mass times my acceleration due to gravity. So Fg, the weight, must equal 15 times 9.81, which if I grab my calculator equals 147.15 newtons. This is weight, so that means it's going to be pulled downward. And that's, as I said, where I like to incorporate the negative. You could certainly put negative 9.81 and get a negative value, same thing. But I think you'll find if you use 9.81 and you use arrows to represent the direction, I think as we move forward into more material, that's something that will help you. But by all means, do whatever makes sense to you. All right, the same mass, it's still 15 kilograms. I haven't kind of chipped off any molecules. On the moon, I'm going to use the same equation, but the weight of that object on the moon is going to be its mass of 15 kilograms, in this case, times the much lower acceleration of 1.67. And we would expect things to weigh less on the moon, and in fact, they do. That same mass on the moon will only weigh 25.05 newtons in the downwards direction. All right, it is a fairly straightforward equation, a fairly straightforward calculation, but it is one that people forget to make sometimes. They plug in just the weight or they plug in just the mass. All right, let's look at one more. I would pause the video. I'll explain this real quick. Pause the video, see if you can solve this, then I will work through it and you can see if you did it correctly. Now, the diagram's a little bit hard to see what's going on there, so what we have here is we've got this block right here. This is a 20 kilogram block, and it's been placed on a scale. So we've got a 20 kilogram mass, and we're being shown that the weight of that block, okay, is 100 newtons. Now, this is not Earth. This is not Earth. So the weight of that block, or the force of gravity, is 100 newtons, and the mass is 20 kilograms. If we have this information, we should be able to figure out whatever planet or location we're in, what is that acceleration due to gravity? We know it's not 9.81, so we're going to try and find it. Pause the video, see if you can solve it, and then let's see how well you did. All right, so I'm going to list what I'm given. The mass of this block is 20 kilograms. We know that the weight, which is the force of gravity, is 100 newtons. And we are looking for the acceleration due to gravity. So we can apply our adaptation of Newton's second law. The weight is equal to the mass times the acceleration due to gravity. I could plug numbers in. I kind of like to take a shortcut. I say, well, if I divide both sides by m, that will cancel that out, and that gives me that Fg over m equals the acceleration due to gravity, which kind of makes sense. To get the weight, I multiply mass times 9.81. Then to go backwards the other way, I'm just going to divide. All right, so my force of gravity is 100. My mass is 20. So we should be able to figure out here that the acceleration on this planet is 5 meters per second squared, acting in the downwards direction.